Okay, let's start. So we'll quickly go over the overview of what was covered this week. And one common question was coming up in this L effective calculation. So one common question was coming up again and again in the forum. Like, sorry, I'm late in answering, but I'll answer this, and I hope there will be no more doubts after that. So this week was covering nonlinear effects in single mode fiber, and we also introduced the components that we use in a communication link. So our discussion on nonlinear effects continue from last week. Last week we covered the basic concept of nonlinear refractive index and self-phase modulation. And in the same equation, when you consider two propagating waves, we encounter cross-phase modulation and four-wave mixing. We did not go too much in depth about four-wave mixing, but that is can be a useful application in some emerging applications. Then this is the first place we talked about this phase matching also. How phase matching will ensure that nonlinear effects are like more prominent, and how in a communication link the dispersion is acting against phase matching. So due to dispersion, like this effect of four-wave mixing will be lowered. Then we went on to discuss about the other nonlinear effects, which are the scattering effects. So previously we had encountered Rayleigh scattering, which is a linear scattering. So if some wavelength gets scattered, the scattered light will also have the same wavelength. In contrast, Brillouin scattering and Raman scattering will give rise to different wavelengths compared to what was incident. So Brillouin scattering was caused by these acoustic phonons, and Raman scattering is caused by the molecular vibrations, which some sources also call as optical phonons. And we also talked about how Brillouin scattering in an optical fiber is allowed in only one direction, counter propagating to your wave. And okay, this is spelling mistake. Like SBS will limit how much power you can transmit through a fiber. Like after some point, your receiver will not receive all of the transmitted power. It will most of the power will get transmitted back due to SBS, stimulated Brillouin scattering. Typical values you should keep in mind are like the effect will become prominent after this 10 milliwatt or 10 dBm of optical power. In contrast, Raman scattering will start at higher levels of powers, but it can be used in some specific applications for amplification. And then we talked about this nonlinear Shannon limit, how it is not necessary that if you keep increasing the transmit power, you will have a better capacity. So with this, we closed our discussion on nonlinear effects and went on to discuss about different optical components that we commonly encounter and some of the performance metrics that you keep seeing again and again. So we started our discussion using with our directional coupler, which is a very ubiquitous component you'll keep seeing again and again. And in next week, we are discussing coherent communication. There you'll be using this 2x2 directional coupler. Like you will be using the expressions. Then we also, after discussing how to construct these 2x2 directional couplers, we also told how n cross n or star couplers can also be made, and they can be used as some WT multiplexer also. Then we talked about variable optical attenuator, polarizer, and polarization controller. Basically, we discussed about the constructions and polarization controller. Again, you will be encountering when you make a coherent receiver. So polarization controller you make using three pedals, basically three plates, one quarter wave plate, one half wave plate, and one another quarter wave plate. Same concept goes to free space optics also, like polarization controller. Then we talked about some non-reciprocal devices. We talked about Faraday rotator and how Faraday rotator and birefringent walk-off blocks and what was the other? So we just talked about the construction of isolator and circulator, how they are made using these non-reciprocal devices. And then we went on to discuss about fiber Bragg gratings, wavelength filters, and how they can be used to make optical add-drop multiplexers. And we finished our discussion about components with this wavelength selective switch. So the equations from last week are these, like how flux density and electric field are related, how polarization of the material is expressed. So in optical fiber, we ignore this term. Then here we encounter this effective length, and I think some people were confused about this expression. Then we went on to discuss about this cross-phase modulation, how this cross-phase modulation is has a like 2 times the contribution to phase change at our desired frequency. Then phase matching condition for 4-way mixing. I think this equation was mistakenly given in week 6, some question number 8 or something. So like this is where that question came from. And then we talked about relevant scattering, like what kind of frequencies you can expect in a free space or in some fluid, what you can expect, and in what kind of values you can expect in optical fiber. So you will have a peaks offset by this much from where you're sending your signal. And then the SBS threshold, after which this after which power the SBS effect becomes prominent. So I think there are multiple questions in this week's assignment based on this equation. Similarly for Raman scattering, this equation. Then some equations regarding components, how to make couplers, how this transfer matrix you can consider, like if E1 and N2 are the input electric fields, what are the output electric fields you can express in terms of this matrix. You'll be seeing this like epsilon equal to 0.5. That becomes a 3 dB coupler. You'll be seeing this next week also. Then some equations, some relations, definitions about this performance metrics of these devices. So there you like all of them are relating powers. Some are relating how much output power you're getting for how much input power. Some are relating how much like unwanted power you're getting at some port. So those kind of relations. All of them follow this basic equation. But depending on the use case, you will have like different names and then from fiber Bragg grating, you get this this equation telling you what are the wavelengths that are getting reflected and what else are like what are getting passed through. And in polarization controller, we saw this kind of equation, like how much birefringence you are introducing using some bend radius of R for like, fiber radius of this. So these are all of the equations that we encountered. Most of the assignment for this week are based on this. You have to find L effective using this equation. And some of the component questions there, I hope there isn't much trouble. Not everything is directly from the classes, but I hope you can find the solutions. Before looking at the few data sheets, and like in class, ma'am showed these components, but they were like in the corner of a video. I don't know whether you saw the components properly. Go visit some vendor websites. But the size of the components, I hope you got the idea of like how big the components are. Yeah, so this question was asked like multiple times last week also, this week also. So L effective was defined as this equation, and alpha is given either as this 0.2 dB per kilometer, or in one question, this instead of 0.2, they're using some other values. So there, like the only mistake you guys are making are this alpha you have to express in linear scale. So so how does a wave attenuate over some distance? So if we started with amplitude A0, after some distance L, you will have amplitude A0 e to the power minus alpha L. And here, like instead of giving, so if you see the units e raised to the power minus alpha L, so this has to be some unitless quantity. It's basically we call as NEPER, e raised to the power some unit, e raised to the power some number. That number we call that as having unit of NEPER, and L will have unit of some meter, some length. So alpha will have unit of nepers per meter. So when you do alpha times L, you have nepers per meter multiplied by meter. That will give some unitless number. So instead of giving this alpha in nepers per meter, the figure that we know, the value that we commonly use is this 0.2 dB per kilometer. But how do you convert it back to nepers per meter or nepper per kilometer also, like if you find that more convenient? But you have to make sure that you're converting it back to SI units, linear units. So what this alpha is equal to 0.2 dB per kilometer, what is it saying is dB will always give some ratio. So what it is saying is 10 log base 10 of this, this is a naught e to the power minus alpha L divided by a naught. That is this. This is equal to 0.2 if L is equal to 1 kilometer. So this is what is given. This is what you know. So from there, you have to find out what is alpha in nepers per meter. So these are the simplifications. Like it will be minus alpha L we have put 1 kilometer, and then this 10 raised to the power minus 0.2 by 10. From here, like you find alpha equal to, like it will come out as 0.046 nepper per kilometer. So even in the questions that follow the video, like you will find the answers correctly if you use this value, like so this is like a MATLAB free version of MATLAB. This is Octave. Works syntax is similar to MATLAB, but it's like free and open source, and also it's like less powerful. Here the answers that you were looking for are like end of the video examples were these ones. Like what is the L effective for 10 kilometer? You put it in this equation. We're putting in this equation. So 1 minus e to the power minus alpha L divided by alpha. So 1 minus e to the power minus alpha L divided by alpha. Alpha in nepers per kilometer here. This is 10 kilometer. So that is coming as like 8 kilometer is the effective length. Then when you go to 100 kilometer, the effective length is 21 kilometer. At 1000 kilometer also is 21.74 kilometer. So there aren't mistakes in the provided answers. Similarly, there were questions about this. I think Soumya asked about this. Are the options correct in assignment 10 questions 1, 2, 4, all those? There also you have to convert it to nepers per meter, and then like it will match with one of the results, like after multiple choice. So there also you find this L effective and then apply this threshold for pretty straightforward questions in that section. Are there any other doubts?
Sir, can you show the MATLAB screen again? Sir, what are the answers? Please tell again for 10 kilometer, 100 kilometer and 1000 kilometer.
So for effective length calculation, you'll be using 1 minus e raised to the power minus alpha L divided by alpha. This alpha you're putting in nepers per kilometer here. It's put in.
Yes, sir. Oh, answer is
but
21. Okay, understood.
So like you cannot put it in dB per kilometer. You have to convert to linear scale and then put. That's all. And the conversion is like happening like this. If there are more doubts, keep them coming. Meanwhile, we will go shopping. So, so you saw in the videos like how the components look like. But if you want a closer look, like this is a, I think Australia-based vendor. They sell optoelectronic components. So they sell is like this is a 2x2 coupler, and you can buy with connectors and all. What they look like is this. So all of the optical components are inside this metal tube, which is sealed. Like you don't tamper with that, and outputs will have these fibers. These are like encased in some plastic. So, and the connectors will, for lab purposes, what you will see are connectors like these. So, what you have are like the fiber is inside, and for help in connecting, you will have this. You will screw it into the what is the receptacle? Like, so you'll be connecting it to something that supports this connection. These are, I think, FC APC. They're called the connectors. So basically, you have this fiber and fiber core, and around it you will have like other fiber will be only 125 micron. No, you will have other support to make it usable. Like you can plug into different components and use it. So some of the like some of the fibers will be FCPC, they will say, which is like polished connector, which will have a flat edge. But because it is a like it is open to air and this is glass, so like at the boundary there will be this Fresnel reflections. To avoid those, like what is more common in say our lab is it will be angle polished connector. This is some at some sorry, not 80 degree, 8 degree angle. At some 8 degree angle, so this reduces the reflection quite a bit. But to connect two such connectors, like you need to align the other connector also. So like in this picture, like there will be a notch in this connector to align the two fibers. So like these are the connectors, and the main component almost always without fail looks like this inside a tube. If you want to look at some like performance parameters, like they are boasting that insertion loss is low, like only 0.35 dB. Isolation says like unwanted signal doesn't go to the other port. So if you want, you can look at this oemarket.com. You can check. And other reputable companies are like Horlab sells components. Then there is one German website called Hapit. They also sell, but they usually only provide the specifications. Like you won't see any photos there. So this is a fiber Bragg rating. They have given what are its transmission parameters. So at some notch, like it doesn't transmit. That part gets reflected. And it looks like just a fiber. Like this small part is the FBG part. Specifications. Like these are the specifications if you want to look at. Then here's how a circulator looks like. Same, the package looks the same. So the package looks almost the same. Everything will be inside the this tube, and you will have access to all these pigtails. Notch is not clearly visible, but here you can see a notch. So like these are the typical components you'll be seeing. For like consumer applications, you may see different connectors compared to these. So instead of FC APC, you might be seeing SC, the subscriber connector, which is without this screwing mechanism. Like it will be like push into plug, and then you can use it. But like they're not meant to be used like plugged in, unplugged, and like they're not meant to be connected and disconnected again and again. So these connectors last longer. And so far we saw this first on this OE market. You can also see this. This is Thorlabs. They also sell the same components. Components look the same. And if you want to, like, you can go through Thorlabs website, and if you want to look at these components, how they look like, you can see there. Will also get an idea of prices and all. Thorlabs and OE market both publish their prices along with the components. So For example, like this is a variable optical attenuator. This is manual VOA. So you turn this screw and it will affect the attenuation. And they cost like nearly $1,000 per component. And there's a question in chat that if there are any previous year live discussion sessions. Actually, last year we did it in Google Meet without any live streams. So, like, at least for last year, there is no recording. I don't think. Assignment questions also, like, I mean, I don't think we have assignment questions, but the practice questions after the videos that you will have. And this is September 4th, September 24th session you're saying, that is also, I think, from 2 years ago, I think. So from last year, there is no material, I don't think. And go to the assignment questions, like that much is sufficient. If you really want to, you can look at the books. So, on YouTube side, I don't see any questions. If there are no more questions, we can close. And this alpha in like this derivation, I'll be posting in this forum also, wherever the question was asked. Like I'll be copy pasting this. Although there are like too many questions in the assignment, I hope they're not like difficult or time consuming. Yeah, repeating the same concepts again and again. So. Okay, let's close. If you have any doubts, you can post in this forum. I'm being lazy at answering all of the questions. I think some questions from last week I have not answered, but by tomorrow I'll try to answer. Okay. I mean, I'm seeing the questions and all of the, like, if there is any time sensitive thing I'm doing, but otherwise I'm being lazy. So sorry. Okay. See you next week then.
Thank you, sir.
Next week we are talking about this coherent communication. No, so I'll try to also briefly show some MATLAB simulation, if possible. I'm not promising anything, but we'll try to show some capabilities of MATLAB. Okay.